Let's have a look at page 1 of your EM induction worksheet. So June 2018 P42, state what is meant by magnetic flux linkage of a coil. So magnetic flux linkage, you've learned in the previous lesson, is either N phi or NBA, because you're substituting the phi here with BA here. So if it comes to the definition, you would probably need to use this one. Okay, when you say magnetic flux linkage, is the number of turns on the coil multiplied with your magnetic flux density and your cross-sectional area, provided that the cross-sectional area is actually normal to your magnetic flux density, or your magnetic flux density is normal to the area, whichever it is. So this is one definition. There's for 3 marks. Then if you move on to part B, a coil of wire has 160 turns and a diameter of 2.4 centimeter. The coil is situated in a uniform magnetic field of flux density 7.5 millitesla as shown here. The direction of the magnetic field is along the axis of the coil. The magnetic flux density is reduced to 0 in a time of 0.15 seconds. Show that the average EMF induced in the coil is 3.6 millivolts. So in your case, you want to find out the EMF that has been induced inside this coil here as a result of your flux density being reduced to 0. So there's a relation between flux density and flux. If your flux density is reduced, that would have meant that your flux is also reduced, which in turn would then mean that there's a rate of change of flux. You would have EMF induced. You want to show that the EMF induced is 3.6 millivolts here. So in your case, how do you find out that value? Just let me clear this thing off. We know that EMF is rate or change of flux linkage, which if you expand out the flux linkage equation, you get change in NBA time divided by your delta T. Now, there are certain things that are constant from this expression here, that one being the number of coil turns as well as your cross-sectional area. So you can actually just bring them out, so that your eventual equation becomes change in flux density divided by time. This one will also give you your EMF. So your number of coil turns is something that you already know as 160 turns. And then when it comes to your cross-sectional area, since you're given the diameter here, your area is thus pi over 4 d squared. You can find out the area from that. And then when it comes to the change in flux density, you already know that it's changing from 7.5 millitesla to 0 in a time of 0.15 seconds. So you already know these values here too. So all that's left for you is really just to submit whatever you know. So EMF being n times pi over 4 d squared times change in flux density over time will give you these values over here. Just remember to change out your centimeter to meter and don't forget the square. Eventually, you get your answer as 3.62 times 10 power minus 3 volts. You want to change it to millivolt, you just need to divide by 10 power minus 3. Then you get 3.6 millivolts. So that one is pretty straightforward here. For your case here, they didn't really say anything about magnetic flux density is reversed in a time of some second. If you see that the question says that the flux density is reversed in a certain amount of time, then you know that you definitely need to multiply by 2 from what you saw in the previous examples in the last lesson. So now if you then look at C, this one is regarding some sort of graph plotting again. The magnetic flux density B in the coil in B is now varied with time as shown in this figure here. This is the variation of flux density with respect to time. So for what I mentioned to you last lesson, almost always whenever you're trying to plot a graph of EMF versus time from a certain given graph, it's always going to be the gradient of the graph itself. As to why is it always the gradient of the graph, in the last lesson, I showed you a few derivations as to why, but you're not required to show it inside your exam. you're not required to show it as part of your working. So here, how do you know that a graph of flux density versus time, the gradient will be equals to EMF? You can actually relate back to what you've actually done in the previous question, where we originally said that EMF was actually rate of change of flux linkage. The flux linkage, you expand out the expression to become change in NBA divided by delta T. If your number of Coulomb turns and error is constant, that would in turn mean that this and this can be disregarded, so that EMF is thus proportional to rate of change of flux density, which is in turn the gradient of your flux density versus time graph. That's how I know I'm going to get the gradient here. So here, certain sections of interest to you would always be the part where you have zero gradient, this, zero gradient, zero EMF. And then after that, you have this other part here. Your gradient is constant, but right, your EMF should be constant. In your case, it should actually have been 3.6 millivolts. So how do I know it's 3.6 millivolts? Again, your questions will often give you a hint about that. Usually before you do your graph plotting, you will notice that the question right before that is asking you to find some sort of EMF value. So in your case here, they told you that your flux density was reduced from 3.6 millitesla to 0 in 0.15 seconds. So that your EMF produced was 3.6 millivolts. So bearing that in mind, you look at what you have at your graph right now. This one is, oh sorry, it's not 3.6 millivolts, sorry, my mistake. It's actually 7.5 millitesla. This is not 3.6. This is 7.5 millitesla. So if you now look back at your graph here, this value here is actually 7.5 millitesla and is going to 0 in a time of 0.15 seconds. So this particular section here has already been represented over here in something that you calculated before, where you say that the EMF value is 3.6 millivolts. So that's why here I can actually say that gradient constant, EMF constant, the EMF is really just 3.6 millivolts. Then after that, the next part here, this is where a lot of times people get it wrong. You can see here that the gradient is constant. And then sometimes, because of the previous questions that we've done so far, where your second EMF, we always say is opposite gradient and so on and so forth. So your EMF will be in opposite direction. If you look carefully for this second part of your slope portion here, your gradient direction is actually the same as that before. Same gradient direction. Because this is pointing down, this is also still pointing down. So your gradient direction here actually did not change. Unlike the previous examples that we did in the last lesson, the second EMF was always having an opposite gradient. So your EMF will be having a negative. Here, gradient direction still remains the same. So you're not going to have any opposite EMF. Now, then after that, when you're talking about your magnitude, gradient constant, same direction. Now, then after that, when I want to talk about the magnitude of my gradient, I can clearly see it's not going to be of the same steepness. How do I know whether this is going to be steeper or less steep? So it's the same thing as what I've done for you last time. Gradient being the change in y value over the change in x value. You just look at your graph now, which one is actually the same? Is it the change in y or is it the change in your x? This one is 3 large boxes. This one is your change in y. This one is also 3 large boxes. It's also your change in y. You could say that your change in y is the same for both gradients here. So now I can then say that delta y being constant would mean that gradient is inversely proportional to change in x. So now I'm interested in the changes in x. Here you can see that your change in x was actually this one, 0.15 seconds. And then as for this one, you can see that it's about half the value. This one, your delta x is about half the value. I mean, if you count the boxes carefully, you will notice that it's actually half that of here. So if your delta x is actually smaller by 2 times, your gradient by right should be increasing by 2 times. So your gradient here is constant, twice as steep. Therefore, your EMF will be constant and double. So your EMF here is 7.2 millivolts. There's no negative here, all right? Because you are having your gradient in the same direction. So you now want to put in your values. The blue color section here being your zero EMF is here, here, and here. Okay, and here. And then after that, your first EMF being 3.6 millivolts is here. Second EMF being 7.2 millivolts, it will be here. So just remember to join the lines together like this. And you would be fine. So if let's just say you read your graph differently, like this, for example, this one will also be okay, right? Where you read it like this, it's also okay. As long as you show that your EMFs are in the same direction, then that one should be fine. Have a look at page 33. 33 would have been November 18 P41. So if you look at that question on the page 33, November 18 P41, state Faraday's law of electromagnetic induction. This one is something that we've done quite a few times already. Magnitude induced EMF is directly proportional to rate of change of flux cutting or rate of change of flux linkage, or you can actually just replace it as EMF is equals to rate of change of flux. That's all. This is the simplest as it can get. The key thing to note is always you saying rate. All right. When you say rate, is always per unit time already. That's the actual definition of how EMF is induced. You need to have rate of change of flux cutting, rate of change of flux linkage, rate of change of flux. Now, then look at part B. B here says that a solenoid S is wound on a soft iron core as shown in this figure. Core C having 120 turns of wire is wound on one end of the core. The area of cross section of core C is 1.5 centimeter square. A hole probe is close to the other end of the core. When there is a constant current in solenoid S, the flux density in the core is 0.19 Tesla, and the reading on the voltmeter connected to the hole probe is 0.2 volts. The current in the solenoid S is now reversed in a time of 0.13 seconds at a constant rate. For part 1, calculate the reading on the voltmeter connected to coil C during the time that the current is changing. So if you look at your question here, you actually have two different coils or solenoid. The first one is actually your solenoid S here, and then the other one is your coil C here, which is then connected to your voltmeter. So, and then the other end here is your hole probe. So from this diagram here, your voltmeter here for coil C is meant to measure your EMF induced, whereas the other voltmeter connected to your hall probe is to measure hall voltage. In other words, it's meant to detect your flux density. So If your switch is closed, current by right will flow like this, maybe like this, and then coming back out to your other terminal. The moment you have current flow through your solenoid from the magnetic field chapter that you've learned before this, as long as you have current flowing through a solenoid, you will produce a magnetic field around that solenoid itself. So let's imagine that the solenoid is having a magnetic field that looks like this. And it extends all the way to core C as well as to the core probe. The reason for that is because you actually have an iron core here. The iron core can be thought of as strengthening and extending the field. The iron core strengthens and extends the field. Extends the B field so that you have this situation that is shown here. All right. Now you want to find out the EMF induced, the reading on the voltmeter connected to coil C. Find out the reading on the voltmeter connected to coil C is actually trying to find out the EMF induced. All right. When the current is changed in direction for 0.13 seconds. So over here, you see something is being reversed here. More or less, you're going to have to multiply something by 2 again. So you refer back to the very first definition of your EMF induced, rate of change of flux linkage, change in NBA divided by delta T. You know that number of coil turns and your area is constant. You're gonna get something like this. N times A times change in B over delta T. So right now, this is how you will get your EMF out. Then how do you proceed from here? For your case, they already did tell you that your flux density is of 0.19 Tesla. You see here, they already told you that when there's a constant current in solenoid S, the flux density in the core is 0.19 Tesla. So you can imagine that right now, this flux, this magnetic field that you have here has a flux density of 0.19 Tesla. And maybe say, imagine that the direction is going downwards like this. This is the direction of magnetic field with your magnitude. But when your current is reversed, you are still going to get that same magnetic field pattern across your solenoid, which then extends to core C. But this time the direction will be opposite. You'll probably go like this. When your current is reversed, your field direction will reverse, but your magnitude still remains at 0.19 Tesla. So your B field direction reverses. So now if you are then to plot a graph of say flux versus time, P versus T, it probably looks something like this now. You want to find the change in flux. So here I could say that this was 0.19 Tesla. This is negative 0.19 Tesla. Maybe this one I want to put negative just so it's a bit clearer. This is negative 0.19 Tesla. So your change in flux density here is really just 2 times of 0.19. Okay, maybe I draw it the other direction. This one here is 2 times of 0.19. This is where your 2 came from. I'll just write it here. So this one you will put inside here. So now if you want to put in all your values, this is how it looks like. EMF being rate of change of flux linkage divided by time, change in MB divided by time, then you put in the value of your number of coil turns times with your flux density multiply with 2, then multiply with your cross-sectional area before dividing by 0.13 seconds. Your time when your flux density reverse was given as 0.13 seconds. Yeah, one thing to be careful about is your units again. 1.5 centimeters square, you need to change it back to meters. So times 10 power minus 2 meter square. So it's 1.5 times 10 power minus 4 meters square. That's why there's a 10 times 10 power minus 4 here. So eventually your EMF value will give you 0.0526 volts. Okay, now for part 2, in your table here, complete the figure, complete the table for the voltmeter readings for the times before, during, and after the direction of the current is reversed. So you are supposed to fill in the values for the voltmeter connected to coil C and for the voltmeter connected to the Hall probe. This one, as I mentioned to you, was trying to read the EMF. And then the other one was trying to read the Hall voltage. In other words, it was trying to detect your flux density. This one was trying to find out your EMF induced. Right, so let's go through this column by column. Before your current change, what can I say before current change? So if you're talking about before current change, current was constant. Therefore, you have no change in flux. Your EMF would be 0 because the diagram that was given to you was this one. You had your solenoid, and then you had your coil C, and then after that you had your coil probe here. When you had current running through your solenoid like this, you had a magnetic field produced that looks something like this. So because your current was constant, your current hasn't been reversed in direction yet. It's still a constant current. So current was constant. There's no change in magnetic flux because your magnetic flux was probably in a direction like this. I'm sorry, just now I draw it downwards for you. So let's just maintain some consistency. So current constant, no change in flux, EMF is 0. All right. But at the same time, because your flux remain constant, your B is constant, therefore Hall voltage is going to be constant too. So the value of your Hall voltage is actually given here in your question itself, 0.20 volts. When it comes to the EMF induced, it's really just going to be 0. So this is the first column. Now, how about the part where you talk about during current change when the current is 0? So here, if you're talking about during current change, this one I'll probably just write here. During current change, your current has actually reversed. So therefore, there is change in flux. You would have EMF induced. Thus, EMF is induced. Which is actually going to be what you found just now in the previous part of your question. In the previous part of your previous part of your question, you already found out that the EMF induced is 0.0526 when you reverse the current direction in this time. So here, you put that value in. Your EMF induced is 0.0526 volts. That's what you have over here. Now, when it comes to your whole voltage reading, this one is a bit different. You can't really say that you are going to have a whole voltage reading here because how your current changes was actually something like this. If I try to translate it into a graph of flux density versus time, it's also going to be like this. So your whole voltage is actually really just measuring this part here, this vertical line here. All right. So it can't really measure all these values here like this. It's just going to be zero. Just think of it that way. Because here, at that instant in time where you are changing the current direction, when current is zero, your whole voltage is actually zero. Maybe I just write it here. At the point where I is zero, there is no B field produced. Therefore, B is zero. Your whole voltage is zero. So the value is here. There's a reason why they say current is zero here. It's mainly meant to tell you that if you just focus your attention at the point, at that one point in time where your current change and pass through zero, that point where it passes through zero, there's no field produced. So flux density is zero, whole voltage is zero. And then after that, what about the last part where you have after current change? Okay, now after current change is probably going to be the same as this, just that there's some slight differences. So here, after current change, what you have is also current constant, but opposite direction. Okay, this one here, I'll just write it here. After your current change, your current is constant, but opposite direction. Therefore, flux is opposite, but there's no change. Flux is in opposite direction, but there's no change in flux. Flux is in opposite direction, but no change in flux. So your EMF would be zero because there's no change in flux. That's why you get zero right over here. And then after that, when you talk about the second part about the flux, so your flux is constant, opposite direction. Flux is constant and opposite direction. Therefore, your B is constant and opposite direction. So if you want to make a conclusion, then therefore VH is constant and opposite. So rather than having it at 0.2, you're going to have it at negative 0.20. Because if you try to imagine what happens after your current change, it's basically something like this. Let me try to redraw it here. Okay, I just probably just use the same diagram here. If your current has actually changed, your flux direction will reverse. of few direction would reverse, same thing. Okay, so this one here, I'll just write it as your direction reverses when current reverses. You can relate this to what you have over here for the third point. Right, so that should be it for this question. Just one more question to go through before I go through the explanation questions. Next question that you can have a look at is actually page 34. It's actually the one immediately below here. So I'll clear this diagram here. If you look at that question under page 34, it's the same page as the table that you just completed. November 18 P42. A hole probe is placed near one end of a solenoid that has been wound on the soft iron core as shown in this figure. The current in the solenoid is switched on. The hole probe is rotated until the reading of the hole voltage on the voltmeter is maximum. The current in the solenoid is then varied, causing the magnetic flux density to change, and the variation with your time or the magnetic flux density B at the hole probe is as shown here. So for the next part, they mentioned that the hole probe in A is now replaced by a small core of wire connected to a sensitive voltmeter as shown in this figure here. The magnetic flux density normal to the plane of the small core is again varied as shown in figure 9.2. So on this figure below, draw a line to show you the variation with time t of the EMF E induced in the small core for time 0 to t equals to 4. So again, it's asking you to plot a graph of EMF versus time. This one, by right, again, you should actually just use your gradient again, all right? Based on what has been described here, you are most likely going to use a gradient again. So before I go through explaining why is it your gradient again, let me just go through some parts of your question here. So in your case here, you had a solenoid, or rather a coil like this now. This is your coil. When current ran through your circuit, you produce a magnetic field that looks like this. For the first part of your question, what you did was that you place a Hall probe to measure the variation in your magnetic flux density. They told you that they go and vary the current inside your solenoid, which then causes your magnetic flux density to change. So when they try to measure the magnetic flux density by using your Hall probe, this is what they got. This is the variation of your flux density versus time. So from there, after that, what they then did was that you again have that same coil through which the same current is running through. So you are actually going to produce back that same magnetic field. So that when you then change your current, your magnetic field varies in exactly the same manner as the one here. But this time you remove your Hall probe and you go and add some sort of coil over here, which is then connected to a voltmeter. So here, since your flux changes, your flux density change, this one your flux density changes, you can also say that your flux changes. Therefore, there is rate of change of flux and hence EMF is induced. You can recognize that there's a change of flux here, rate of change of flux here, hence EMF will be induced. Your voltmeter here in your other coil is meant to measure that EMF induced. So here, why do I say that I can actually make use of the gradient to find out my EMF? This one, again, you relate it to EMF equals to rate of change of flux linkage where this becomes delta NBA over delta T. Your N and A are constant. This would mean that EMF is proportional to delta B over delta T, which in turn is actually EMF proportional to the gradient of your BT graph, like this. So this is the relation that you would want. So now you can just look at your gradient and just work out the answer. So to save your time, next time when you go through your exam, just remember it's always the gradient. Okay, I have yet to see another different case where they don't use the gradient. So this one here, gradient 0, EMF 0. This one here, gradient 0, EMF also 0. This part here, gradient constant, EMF would be constant. So you expect your graph to look something like this now. It's probably going to look like this if you try to translate what I just drew earlier. There are certain regions where EMF is 0, which is this part. And there are certain regions where your EMF is constant, which is this part. The magnitude doesn't matter. There's no information given inside your question that will allow you to find the magnitude of your EMF. So you just leave it as it is. Okay, they did give you the value of your flux density, but they never gave you any information about the time. So you won't be able to work out what is your flux density in the first place. You won't be able to work out what is your EMF in the first place. So it's just going to be this graph shape that you see here. Okay, right. So this covers the part where you're talking about graph plotting and EMF calculation. The next part of your past years will normally deal with your state and explain question. This is where sometimes the difficulty in the chapter comes from.